Hi friends, today we will be discussing the combinational logic circuits. So initially we will be starting our discussion by pointing out the difference between the combinational and logic circuits. So our first topic is the table of differences between combinational and sequential circuits. And then today we will be discussing all the adder concepts, right, starting from the half adder, full adder, then parallel adder, BCD adder, and one important topic called carry look ahead adder. So today our topic of discussions are half adder, full adder. Then we will be constructing a 4-bit parallel adder. It is also referred to as ripple carry adder in many of the textbooks. We will also try to justify why it was given that name. So then we will be constructing a 4-bit BCD adder. Similarly, these concepts can be extended to higher bit adders like 8-bit and 12-bit and so on. And one very important adder, it's called as the carry look ahead adder. It is the fast adder when compared to the ripple carry adder. We'll also give the proper justification of why it is fast, and in terms of the numbers and in terms of the delay of the gates, we'll try to justify its fastness when compared to the ripple carry adder. So these are the topics that we'll be discussing today, and in the subsequent sections we will be covering the remaining topics. Those are everything related to subtractors. So that is half subtractor, and similarly there is something called full subtractor. And similarly the parallel subtractor. Like BCD addition, there is BCD subtraction. But this can be performed in both the ways. So we will be having two different logic circuits for BCD subtraction. So one is performed by using the 9's complement method, and one is performed by using the 10's complement method. We will see both these methods. And in addition to this, there were very important combinational logic circuits. So those are encoders and their complements, decoders. And similarly we have multiplexers. In short, they are referred to as muxes. And similarly we have demultiplexers. And one more important topic called as the code converters. Code converters are the circuits that converts the code from one number system to other number system. Let's say, like example, let's say we have a number in the binary format, and we were asked to construct a combinational logic circuit that converts this binary number to some, let's say, XS3 code. So these types of conversions are being performed by these code converters. We will try to build some combinational circuits of this conversion. So like we can also convert the XS3 code to binary code, and let's say if we were asked to convert to BCD, then we can do it from XS3 to BCD, and similarly from BCD to XS3, and from BCD to binary, and from binary to BCD. So like this. And there is also one topic called as the magnitude comparator. It just compares the magnitude of two numbers, and it will provide an output whether they are greater or lesser or equal to. So this we will be discussing. And there is one more topic called as the serial adder. Actually it is a sequential circuit as it employs a flip-flop, but we'll also see this thing in this section. So today we are limiting our discussion to only these topics today. So let's start our discussion. So let's start our discussion by pointing out the difference between the combinational versus sequential circuits. The combinational circuits are the circuits whose present output depends only on the present inputs. So let me write the basic definition first. So these are the logic circuits whose present output depends only on the present inputs. Whereas a sequential circuit is a circuit whose present output, let me write it as PO, it depends only on the present inputs PI as well as the past outputs. Let me denote it as PO, where PO minus this PO minus represents the past outputs. So the sequential circuits are the circuits whose present output depends upon, that is a function of present input as well as the past outputs. So in general sense, a combinational logic circuits can be described as a black box. Let me this black box is generally called as combo logic in many places. So this combo logic, which has some, let's say, n inputs, which are I1 to In, and has m outputs, let's say O1 to Om. It's a black box. So this black box, so there are many examples of combinational circuits as we have discussed previously. So let me write two examples to just point out the differences. Let's say we are considering encoder muxes and so on. There are many examples of combinational circuits. Now to represent the sequential circuit in a general sense, so it is basically a combination of the combinational logic circuit as well as a register, which is the storage element. So the sequential circuit also has a combinational logic block combo, which requires some set of inputs and which gives some set of outputs. Of all these, so only some of them are required outputs, or maybe all of them. So I am writing that as the present outputs. So as we have mentioned here, it is a function of the present input as well as the past outputs. So these are our present outputs. So how can we make them past? Just give this present outputs to a register, which is nothing but a storage element. So that will make the present outputs to the past outputs. So we require a register here with the input as D, output as Q. Let's say some of them will come and store in this register, whose outputs are given as inputs again to here. So these are our present inputs. these are our present outputs. As we are taking the some of the present outputs to a register and whose outputs are given to a combinational circuit again. So these are our past outputs. So this is how we can justify the given definition. And some of the sequential circuits are counters. In general sense, you can say any FSM. Any FSM is a sequential machine. So as we have mentioned here, mentioned in the sequential logic circuits, the sequential logic circuits does require a memory element, that is the register, whereas a combinational logic circuit does not. That's what I am writing here. So a combinational logic circuit do not require memory element. Memory element is nothing but a register, whereas it does require, the sequential circuit does require. So having been said, with these basic differences, we shall start our discussion with let's start the discussion with half adder. So half adder is also referred to as a single bit adder without the carry input. Let's say we are adding two numbers of each 4 bit. Let's the numbers be 5. So in binary it is 0, 1, 1 and 0. Sorry, in binary it is 0, 1, 0, 1, and let's say we are adding 5 with 6, 0, 1, 1, 0. So half addition is only related to the addition of this 1 with 0, that is this bit with this bit. So actually it requires then two inputs, each of single bit. Let's say this let this input be referred to as A, and let this input be referred to as B. So as given in the table, this A and B are our inputs. A and B are our inputs, and sum and carry are our outputs. So these are the inputs and these are our outputs. So as you can see, adding 0 with 0 will result in a sum equal to 0. Similarly, there is no carry. 0 plus 1 is 1, then with no carry. 1 plus 0 is 1 with no carry. 1 plus 1 is 0. This is according to the Boolean addition. So 1 plus 1 will result in a sum of 0 with a carry of 1. So this is the basic half adder circuits that we will be remembering, and we will be constructing the higher adder circuits starting from full adder, parallel adder, triple carry adder, the carry look ahead adder, and so on. So half adder is nothing but a single bit adder circuits that receives two inputs, A and B, and it gives two outputs, sum and carry. Let's see what this black box consists of. So you see sum here, will generate a Boolean expression for the sum. This sum is having 1 for this set of inputs, that is when A is 0 and B is 1. So this is represented in terms of Boolean expression as A bar B. that is A is 0 and B is 1, and there is one more set of inputs that results in a sum of 1, that is A is 1 and B is 0, that is A is 1 and B is 0, so that's why we write A bar. Now you can see A bar B plus AB bar is nothing but the XOR operation, that is A XORed with B. So this is our sum expression. Similarly, the carry you see here, the carry is 1 only for one set of inputs. So this carry equal to 1 for the inputs A equal to 1 and B equal to 1. So the expression for carry will be A is 1, so it is A, and B is 1, so B. So the AND of A and B. So these are our two basic equations of the half adder. So we can fill this black box as A and B, which are given to an XOR gate, that is the sum output, and similarly A is connected to an AND gate that results in our carry. So this is the half adder circuit. So the delay of the half adder, we will be noting down the delay of each and every combinational circuit. So the delay here is equal to maximum of the delay of this or this, since they are in parallel. Whichever is the maximum, the XOR or the AND gate, that results in the overall delay. So we can write the expression as it will be the maximum of delay of XOR or the delay of AND gate. So usually the delay of AND gate is more when compared to delay of XOR. Assuming that we will be straight away writing the delay of half adder to be start our discussion for the full adder. So as we have discussed, since our final target is to add two numbers, so let's say the numbers are 5 and 6, 5 and addition with 6, so it is 5 is represented in terms of binary as 0 1 0 1 and 6 0 double 1 0. So we are looking for this result. So we are constructing the individual bit addition circuits. So as discussed, for the addition of this 1 with this 0, so let's take the other input. Instead of 5 we will take 6. Instead of 6 we will take 7, so this will look well. So for the addition of these two bits, this one and addition of these two bits, this one and this one, we have employed a circuit called as half adder, which does not require any third input, that is the carry input. But if you see the addition of these two, that is 1 plus 1 is 0, it is resulting in a carry of 1. So now we cannot employ the conventional half adder circuits which require only two inputs, that is A and this input is B. Why? Because we have one more input which was generated from the from the previous half adder circuits. So that is the carry out of that half adder circuits, that will be carry in. So this input we will call as C in, that is the carry in to our circuits. So addition of these 3 bits A, B with this C in is our full adder. So this is a small introduction to where it is useful, and you can see here as there are 3 sets of 3 inputs which each of single bit, so there will be total of 2 power 3, that is 8 combination as it was discussed here. So 2 power 3 that is equal to 8 combinations were there, right, starting from 0 0 0 to 1 1 1. So this ABC, these are the inputs, and so these are the sum and carry are the outputs. Now the truth table for this full adder can be brought or can be derived from the half adder itself. So let's recollect for a minute what we have discussed in the half adder. In the half adder we will be having two inputs, A and B, and two outputs, sum and carry. Now for the input 0 0, the sum is 0, carry is 0. For the inputs 0 and 1, the sum is 1 and carry is 0. For the inputs 1 and 0, the sum is 1 and carry is 0. For the inputs 1 and 1, the sum is 0 and the carry is 1. So this is the truth table for the half adder. This is the truth table for the half adder. Let's see how we can derive the truth table of full adder from half adder itself. Now you can see since for addition of 3 bits, if one of the input is 0, so that input whose value is 0 can be ignored. As you can see here, the addition of 0 plus 0 plus 0, you can actually ignore one so one input which is equal to 0, so that will not change the addition of the remaining 2 bits. So let's say we are for the input 0 0 0, we are ignoring the carry in value, that is 0. So now for this set of inputs 0 and 0, we can directly refer to our half adder table. So this as you can see here, 0 plus 0 is resulting in a sum of 0 and 0. So that is what is written here. Similarly here, the inputs 0 0 and 1. Now you can also ignore one input. Let's say we are ignoring this A, which is equal to 0, and let's see what is the so what this addition results whose inputs are 0 and 1 in the half adder. So for the input 0 and 1, we are having a sum of 1 and carry of 0. So that is what it is written here. Similarly, now here you can ignore, let's say we are ignoring C in. So for 0 and 1, the same thing of 1 and 0. So it was written here. For 0, 1 and 1, obviously we need to ignore this this A input, which is equal to 0. So for 1 and 1, as you can see in the half adder table, its sum is 0 and carry is 1. So that is what is written here, its sum is 0 and carry is 1. And for the input 1 0 0, let's say we are ignoring this C in equal to 0. So A is 1 and B is 0. A is 1 and B is 0. So that is resulting in a sum equal to 1 and carry equal to 0. So that is what sum is 1 and carry equal to 0. Similarly, you can do for this set of inputs and this set of inputs, and there is one set which actually has all the 3 inputs to be 1, that is 1 1, A equal to 1, B equal to 1, and C equal to 1. So that generates the sum equal to 1 and carry equal to 1. This is only one extra addition. So now we will construct a logic circuits for this full adder. So what we are now doing is, so we are constructing a black box. We are constructing a black box which requires 3 inputs. One is A, one is B, and one is carry input. So and it has 2 outputs. One is sum and one is the carry. So let's see what logic this black box has. Now we will try to derive the expression for the sum. Now we can see here we'll try to derive the expression for sum that is equal. Now let's see for what values of the inputs sum is equal to 1. Now sum is equal to 1 for the set of inputs a equal to 0, b equal to 0 and c equal to 1. So this can be represented in terms of Boolean expression as a bar, b bar, c in, and there is three more set of inputs. So sum is equal to 1 for the set of inputs a equal to 0, b equal to 1 and c equal to 0. So a equal to 0, that is a bar, b equal to 1 and c in equal to 0. And similarly we have sum equal to 1 for the set of inputs a equal to 1, b equal to 0 and c in equal to 0. A equal to 1, b equal to 0 and c equal to 0. Similarly we have a equal to 1, sum equal to 1 for the set of 1, 1 and 1, that is a is 1, b is 1 and c in is 1. So a is 1, b is 1 and c in is 1. So now we need to do the Boolean optimization here. So we can take common c input from these two expressions, and similarly we can take common c in bar from these two expressions. So if we take c in common from these two expressions, so that is resulting in c in into a bar b bar plus ab, and from here if we take c input bar as common, bar into, it is resulting in a bar b plus ab bar. So now this is equal to c in into ab plus a bar b bar, that is equal to a x naught with b. So from here if we take c in bar, already we have taken common, so this is a bar b plus ab bar is equal to a XORed with b. So now you can see, you can consider this expression, so you can consider these expressions to be, let's say, some x. So the complement of a x nor b is nothing but a XOR b. So this is nothing but x bar. Or you can consider this to be a XOR b to be x. So this complement, it will be a x nor b, that is equal to x bar. So the sum is resulting in something like c input into x bar plus c in bar into x, which is nothing but again the XOR operation of c input with the x. So this can be written as c input XORed with x. So x is nothing but c input XORed with a XORed with b. So this is our sum expression. So you can blindly remember the sum expression of full adder is a XOR b XOR c in. So this is what our sum expression is, and similarly we will derive the expression for, so let's we will write here this expression of sum. So the sum is equal to a XORed with b XORed with c in. Similarly we will derive the expression for the carry. So So now we'll erase this one. So we'll derive the expression for the carry. So now the carry is 1 here for the set of inputs 0, 1, 1. So this can be written as A bar B C in. Similarly, the carry is 1 for the set 1, 0, 1. 1, 0 and 1. And similarly, it is 1, carry is 1 for the set 1, 1, 0. 1, 1 and 0. This input is 0. Similarly, the carry is 1 for the set 1, 1, 1. The inputs A equal to 1, B equal to 1 and C in equal to 1. So that is A, B and C. Now similarly we can do the Boolean optimization here. So what we will do is that we will take common so now we will be doing its optimization. So let's take A and B common, or so A and B is common between these two expressions. We will take that as common and write the remaining expression as it is. A bar B C in plus A B bar C in. So since we have taken A and B to be common from these two expressions, so it will be C input plus C input bar. As you can see, this will result in a logic value of 1. So this is the basic Boolean optimization, so we can actually ignore this. So now we can ignore this, which results in why, because it results in an equivalent of 1, and 1 into anything is 1. So now the resulting expression is A bar B C in plus A B bar C input plus A B. Now from this we will take A as common, so this will result in A bar B C in plus if you take A as common, then it will be B bar C in plus B. Now again this is one more optimization. If B is here and its complement is there, so the remaining part of B is 1, so that is present here. Obviously 1 into anything is 1, so actually we can ignore this B bar. So this is one important optimization that actually we have seen it in the second chapter. So this will result in the output of A bar B C in plus A into C in, A into C in plus AB. And similarly, if we take B as common from these two expressions, the same kind of optimization principle we need to apply. B into A bar C in plus A plus A into C in. So now we can ignore this A bar according to the optimization. So the resulting expressions are a into b plus a into c plus b into c. So this is our output expression. So the carry value is a into b plus a into c plus b into c. So the black box now, it consists of, in order to derive the sum value, we need to do the XOR of a with b with c. So we require a 3 input XOR gate. So we are taking a, we are taking b, we are taking c. So we require a 3 input XOR gate to generate the sum value, and to generate the carry value we require 3 AND gates, one AND gate for ANDing a and b, one AND gate for ANDing a and c, one AND gate for ANDing b and c, and one 3 input OR gate for so for the ORing operation. So firstly I require the AND of a and b, then the AND of b and c, then I require, I can take the input from here, then I require the AND of a and c. Now these three must be odd to generate the sum value. So this is our black box for the full adder. Now the next important topic is the conversion of or you can say the implementation of the full adder only using half adders and a single 2 input OR gate. So that is what the next topic. So now we will be discussing the realization of one full adder using half adder. Before that we will be writing the expression for the relay of the full adder. So let's again redraw the structure of the full adder. So as you know, it requires 3 inputs, a, b and c input, a, b and c input. The expression for the sum is the XOR of a, b and c. So we require one 3 input XOR gate for this. So this is our expression for the sum, and the carry is a in b plus bc plus ca. So we will take a point from here. This is a, this is b. So one and this, which will compute ab here. Now we will take a from here itself. AC, yeah, and B, we will take C from here itself. So this will result in AC. Now we need to OR these 3 inputs with a 3 input OR gate. So this will result in our carry. So now as you can see here, so the delay of full adder can be the maximum of the delay for realizing the sum expression or the delay for realizing the carry expression. So the delay for realizing the sum expression is nothing but the delay of OR gate, sorry, the 3 input XOR gate. So 3 input XOR, the delay of XOR we will write as T XOR. Since it is 3 input, we write it as 3. So it will be the maximum of this delay or the maximum of the delay for generating the carry, which is equivalent to the delay of 1 2 input OR gate with the delay of 1 3 input OR gate, sorry, the delay of 1 2 input AND gate along with the delay of 1 3 input OR gate. So that will be the delay of one 2 input AND gate. Since it is 2 input, we need not bother about adding 2 here. With 3 input OR gate, so the delay for full adder will be the maximum of these two. Let's say we call this as TFA. So generally we are assuming that the delay of full so the delay of 3 input XOR gate will be lesser when compared to this. So you can actually ignore this, and this will be our critical path delay. So so this is our delay expression for the full adder module. This we will be using in our later sections. So now we will be deriving some expressions where we will prove that we can realize one full adder using two half adders, and we will recollect the sum expression which is equal to A XORed with B XORed with C in. So as you can see, so A XOR B, let us suppose that we have only two inputs A XOR B. So if we give these two inputs to one half adder, it will result in a sum equal to A XOR B, and the result of this A XOR B, if we give to another half adder with the other with one input to be A XOR B and the other input to be this C in, so it will result in the XOR of this expression and this expression. So actually we can so this is the way we require two half adders for the sum expression, and similarly we will see how we require two half adders for the carry expression. So let's recollect the carry equation. The carry equal to AB plus B. I'm calling C input as C, so let's consider it as C itself, and this is CA, so that is AC. Now what I will do is that here let us don't disturb this term AB, and since in this expression A term is missing, so we can add the A term without disturbing the logical equivalency of the expression as like this. So we can add the term A plus A bar. Similarly here in this expression AC, the B term is missing, so we will add the term B plus B bar. So as this B plus B bar equal to 1 and 1 into anything is 1, so this is nothing but AC. So thus we are not at all disturbing its equivalency. So let us keep this as it is and expand the remaining terms. BC into A is nothing but ABC, A bar into BC, nothing but A bar BC, AC into B, nothing but ABC, as we have written already one time here. 1 plus 1 is anyway 1, so we are not at all writing it the other time. And AC into B bar is A B bar C. So now we can take AB common from these two expressions. So AB into 1 plus C, and here we can take C common from here. So C into A bar B plus AB bar. So 1 plus anything is 1, so it is equal to AB, and C into, now we will replace C with C in into A bar B plus AB bar is equal to A XORed with B. So with this, so why we have written this term A, so why we have brought a term of A XOR B in the carry expression? Why? Because this A XOR B is one of the outputs of the half adder. So that's why we have bought this term A XOR B. So let us start realizing uh, the full adder with two half adders. So let's say we have already taken one half adder module. So this is our half adder module. Let's say we are giving the two inputs A and B to it. So we will be getting two outputs. So one is A XORed with B and the other is A into B. Now for the full addition operation, for full adder, we are also having one more input, the carry input C input. Now the sum expression of the full adder is A XOR B XOR C. So now if I give this input along with this input to one more half adder, now the sum expression of this half adder, will result in XORing of this input with this input. So this input is nothing but A XOR B. So the other input is our C in. So this is our sum expression as we have got. Now you can see here this half adder is receiving two inputs, C in into C in along with A XOR B. So the AND operation of this half adder will result in A XOR B into the C in. Why? Because the carry of the two inputs of half adder is nothing but the AND operation, so it will result in the AND of this input with this input. So now what we can do is that we are left with one input here, so that is AB. We can bring this here, and this output, what we can do is that we can do the OR operation of these two input, which will result in our carry. So why we have done the OR operation here? Why? Because we have got the term A XOR B into C input here itself. So this is nothing but this term, C input into A XOR B. So that is this term. So the remaining term is AB, that we have already got from this half adder. So just we need to OR these two inputs. So that's why we are adding this one more OR gate here to generate the carry expression. So thus we have derived one full adder with two half adders and one OR gate. So in the same process we will also derive the delay of this full adder itself in terms of the half adder. So the delay of the full adder in terms of the half adder is so to generate the sum it requires the delay of two half adders, one and this two. To generate the expression of carry it requires the delay of one half adder along with the delay of this half adder and this OR gate. So obviously it will be the maximum of these two, that is equal to 2 times the delay of half adder with 2 times the delay of OR gate. Since it is 2 input, we are ignoring the 2 here. So that is equivalent to, what is the delay of 2 half adders? As we have discussed previously, the delay of half adder will be the maximum of the delay of XOR gate or the delay of AND gate. Obviously the XOR gate will be having more delay when compared to AND gate. So directly we are replacing this half adder with the delay of half adder with the delay of XOR gate. So it will be equal to 2 times the delay of XOR plus 1 time the delay of OR gate. So this will be our expression for the Now we will discuss full adder. The topic ripple carry adder. As we were seeing in the previous explanations of the full adder and the half adder, so we are constantly looking at these tasks of adding, let's say, 5 and 6. So this 5 is represented as 0 1 0 1 and 6 is 0 1 1 0. So I think now we have got now we have enough logic circuits to bring out this task. As you can see here, this we have discussed it previously also. The addition of this bit with this bit, I mean the corner bits, we require one half adder circuits. This can be performed by half adder circuits that we. So this addition will result in, let's say, one sum value, and it will generate a carry value. Now this so now we need to add 3 terms, that is a generated carry along with the 2 already remaining terms. So for these operations so for the remaining operations, so basically all these terms, so as this process repeats, we require a full adder for this. We require full adders for this. So let's see the logic circuit realization of this ripple carry adder. So let's denote this 5 and 6 with 2 inputs, let's say A and B, where the individual bits are represented as A3, A2, A1, A0, and similarly for B, the individual bits are represented as B3, B2, B1 and B0. So now we need to add these 2 inputs, A and B. So for adding these 2 bits, A0 with B0, which does not require any carry input, so we can actually employ a half adder here that requires the input A0, B0. So half adder will have one sum output. Let's denote this as S0. So we will write S0 here. So now this will generate a carry. Let's call that carry to be C1. So this carry that is generated from here, so let's change the color. So this carry C1 needs to be added with the bits A1 and B1. So for this we need to employ a full adder. So now so we need to employ a full adder where our 2 inputs are A1 and B1. So A1 and B1, that is this A1 and B1 along with the carry output of this half adder, that is C1, are receiving the input or the inputs of this full adder that will generate one sum expression S1 and one carry expression, let's call this as C2. So it will generate so this will generate one sum expression as S1. So let's change the color of all this. So addition of these 2 will generate the sum expression S0. This will generate the sum expression S1 and similarly a carry expression C2. Now for this addition we require one more full adder. One more full adder that requires the inputs A2, B2 and the C2 is anyway we are giving here, A2 and B2, that will give the expression S2 here. And let's this carry out be called C3. Now we are left with two more inputs, A3 and B3. So here addition of these two will result in some expression of S2 with carry C3. So we are giving the remaining bits here, A3, B3. We require a full adder that will result in some expression of S3 and carry expression that will be here, that we are calling as C4. So addition of these three is resulting in some expression of S3 with carry out as C4. So this section, this is called as a ripple carry adder. Let's remove this now. Now this is called as a ripple carry adder. You can see we are adding the two operands. So that is the two operands A and B, each of 4 bit, one input being A3, A2, A1 and A0 with B3, B2, B1 and B0. And we are generating the sum expressions S0, S1, S2 and S3. Anyway, this C4, as we are not at all giving it to the remaining stages, so this will also be considered as one of the outputs. So this is our ripple carry adder. So whenever we were asked to realize the ripple carry adder only in terms of the full adder, you can do one thing. What we can do is that, so since this half adder does not require any carry, which means that its carry input is 0, so we can replace this with full adder with carry input equal to 0. So this is the only modification that we need to do. So now similarly we will write the delay for the ripple carry adder. So we will refer this to be T RCA. RCA means the ripple carry adder. That is equal to the delay of 1, 2, 3, 4. The 4 full adder delays. That is 4 full adder delays. So if you are given the delay of 1 full adder, so and if you are asked to find the delay of the ripple carry adder, so that is the 4-bit ripple carry adder, so you need to just blindly multiply it by 4 and it will give us the delay of the ripple carry adder. So now this full adder delay, as we have seen in the previous section, which is equal to the delay of twice the XOR gate delay plus 1 OR gate delay. So that we are now noting here, that is equal to 4 times twice the XOR gate delay plus 1 OR gate delay. That is equal to 4 into 2, that is 8 times the XOR gate delay plus 4 times the OR gate delay. So this is our expression of delay for the ripple carry adder. Or we can also, if you are asked to write the delay expression of this ripple carry adder in terms of 3 input XOR gate and 3 input OR gate, then you can use this expression here, and you just need to replace the delay of the full adder to be this, which is the maximum of these two expressions, and you can substitute there. So this is a ripple carry adder, and why it is called ripple carry adder is that you can see here the carry is rippling. The carry is rippling to the next stages. So this is our first full adder. here the carry output is rippling, or it is given as an input to the next stage, and similarly this the carry output of this stage is rippling to this stage. The carry output of this stage is rippling to the last stage. So rippling, so this is nothing but the carry is being forwarded to the next stages. So this is why it is called as a ripple carry adder. And so as we are mentioning, the basic disadvantages of this type of realization is the carry input of each full adder should wait for the previous full adder. So that is the C out of the previous full adder. So this is why the delay is increasing. So what if we will calculate this carry delays before itself? So that is, we need not have to wait for the delay of this full adder which will generate this scene. We need not have to wait for the delay of this full adder and this full adder for generating C2. We need not have to wait for the delay of this full adder, and this full adder for generating C3. Similarly, we need not have to wait for the generation of C4. We need not have to wait for the delay of this full adder, this full adder, this full adder, and this full adder for generation of C4. So the concept of calculating the carry before the sum addition is performed is the basic idea for the carry look ahead adder. So with this understanding, let us start realizing the discussion for the carry look ahead adder. As we were mentioning, the basic idea for the carry look ahead adder is to realize the addition operation that is free from the full adder. So that is, if we go for if we see the previous discussion of our ripple carry adder, so basically we need to realize our adder which is free from all these full adder modules. That is, our adder should be directly in terms of our basic gates. Why we are realizing in that sense is that as you can see here, for the delay of for realizing this carry, so it is C3. It should depend on the delay of this full adder as well as this full adder. So we need to wait for the total delay of two full adders for realizing this C3. But what we can do instead is that, as we know that C3 is directly a function of A1 B1, A0 B0, and this C1, we can directly realize this C3 in terms of A1 B1, A0 B0, and this C1 instead of realizing it in terms of the full adders. Similarly, for calculation of C4, previously as in ripple carry adder, we are relying on the delay of this full adder, and this full adder, that is 3 full adders. But instead what we can do is that we can directly realize this C4 in terms of A2 B2, A1 B1, and A0 B0. So this is what we are doing, and this is what our approach, and let's see whether this approach improves the delay of adding two numbers of our approach, or the carry look ahead adder approach, to the ripple carry adder approach. So here, since we are talking everything, since we are comparing the ripple carry adder in terms of the full adder delays, so here actually there would be an off adder here, so that we have replaced with FA, that is full adder. And let us call in real time scenarios this C input, which is equivalent to 0, but let us call this C input to be C1, and the output of this full adder, that is equal to C2 now. And similarly the output of this full adder is C3 and C4 and C5. So that is what we are looking, and let us start the discussion of carry look ahead adder. So in carry look ahead adder, so we need to define two terms. One is the generator term. We can simply call it as the term generate. So that is GI. Let us denote it by GI, that is equal to the ANDing of AI with BI, that is AI into BI. So this is our generate term. So let us define it this way. And propagate term. propagate term, let us call it as pi, that is equal to ai XORed with bi. So these are the two terms we are defining, and we will realize all the so actually these are the terms related to half adder. So we will realize all the carries in terms of only GI and PI, but not in terms of the carries. So basically we are looking at the addition of two numbers, let us say A and B. So A is represented in terms of the bit representation as A3, A2, A1, A0, and B is represented as B3, B2, B1 and B0. So basically we are looking at the addition of these two numbers. So as we have said that practically the C input value is 0 here, but since we are discussing or we are comparing the delay of our carry lookup adder in term with the ripple carry adder and everything we are comparing in terms of full adder. So we are adding one more term here, that is C1 here, so which anyway will be 0, and the sum out of this is S0, S1, S2 and S3, and similarly as we have mentioned so this addition will generate a carry that is equivalent to C2, and similarly the C3 and C4, and the addition of these two will generate a carry out that is C5. And now since we are comparing everything in terms of full adder delays, so let's call this to be stage 1, let's call this to be stage 2, and let's call this to be stage 3, and let's call this to be stage 4. Now so for stage 1, if we say for stage 1, or we will directly generate the general value of sum and carry in terms of this i's, that is the stage number. So basically here I is the stage number, so we will calculate the sum value in terms of this ai and bi, and the propagate or the carry term in terms of this ai and bi and ci. So the sum expression of full adder is nothing but ai XORed with bi XORed with ci, that is equal to ai XORed with bi, that is equal to our propagate term pi XORed with ci. So this is our the basic expression of our sum. Let us denote this to be equation number 1, and similarly for the carry expression of the full adder, which is equal to ai bi plus bi ci plus ci ai, that is equal to ai bi plus ci into ai XORed with bi. This we have previously we have derived this expression. You can refer to the previous notes. So this ai into bi is nothing but gi, and ci anyway remains here, and ai XORed with bi is nothing but the pi. So this we are calling as expression number 2. So we'll remember these two expression, sum and the carry expressions, and so these are the two expressions for the sum and carry, everything in terms of their respective inputs. And so let's jump into the realization of this carry lookup adder. as you remember that these are our stage numbers, stage 1, 2, 3 and 4. So as we are focusing basically on anyway the sum will be the XOR of this PI and CI we need not have to worry about, but we need to worry about this carry here. So previously we have mentioned the carry into be C1 here, so that we are replacing with C0. Why? Because it will align with A0 and B0, so this 0, all zeros are here, all ones are here, all twos are here, all threes are here. So we are replacing this to be C0, C1, C2 and C3. This is C4. So and anyway these are our stage numbers. So now we are giving this term Ci plus 1 to our carry. Why? Because if you consider for the stage number 0, that is this stage, so the carry is equal to so the carry equal to C1. So when we replace I with 0, so 0 plus 1 is 1, so this will represent C1. So this is our carry, that is equal to, anyway our I is 0, so that will be equal to G0 plus C0 P0. So that is everything in terms of zeros, why? Because it is of stage 0. Similarly for stage 1, so I is 1 here, that will result in the carry out of C2, that is this C2. So now C2 is equal to G1 plus C1 P1, so everything in terms of 1. So this is what simple modification. So nothing we have done here, just we have replaced all the carry inputs to be this here. So now let's continue our discussion. So for the stage 0, we'll replace so for our stage 0, the carry out, that is equal to C1, that is equal to, or you can directly, we can note the general expression here, so it will be very easy for us. We'll directly note the general expression, that is Ci plus 1 is equal to, that is Ci plus 1 equal to Gi plus Ci Pi. This is equal to Gi plus Ci Pi. So let us consider this to be our general expression. So anyway I is our stage number. So for stage 0, that will give a carry out of C1, that is equal to G0 plus C0 P0. Similarly for stage 1, that is our second stage, so I value is 1 here, that will result in carry out of C2, that is equal to G1 plus C1 P1, that is equal to J1, that is nothing but A1 into B1, and P1, that is equal to A1 XORed with B1. Anyway this we cannot change. We'll replace this C1 with this expression that we have already derived here, that is G0 plus C0 P0, so which is equal to G1 plus P1 G0 plus C0 into P1 P0. So as you can see here, the C2 is redundant of this C1, that is it depends only on A1 B1 here, that is for realizing G1 P1 here. So this C2 depends on A1 B1, A0 B0 and C0. It is redundant of this C2, that is what we have done here indirectly. Similarly for stage 2, which will generate a carry out of C3, that is equal to G2 plus C2 P2, that is equal to G2 plus P2 into, we need to get rid of this previous carry C2, So directly if we replace C2 with this term, we are getting rid of all the carry ins of the previous stages, that is C2 and C1. So we'll replace C2 with this expression. So this C2 into G1 plus P1 P0 plus C0 into P1 P0, which is equivalent to G2 plus P2 G1 plus P2 P1 G0 plus C0 into P2 P1 and P0. Similarly for the last stage, that is the stage 3, which is nothing but stage 3, this will generate a carry out of C4, that is equal to G3 plus C3 P3, that is equal to G3 plus P3 into, since we should not depend on this carry, in other sense we should not depend C3 on the carry on this stage 2, stage 1 or stage 0, that is we should not we should make C3 independent of the C2 and C1. So what we are doing is that we just replace this C3 with this expression. So C3 is replaced with this G2 plus P2 G1 plus P2 P1 G0 plus C0 into P2 P1 and P0, which is equal to G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 plus P3 P2 P1 P0 into C0. And similarly so this stage, so now we have got all the carry expressions which are only in terms of the inputs A3, A2, A1, A0, B3, B2, B1, B0, but are independent of the intermediate carriers. So this is
basically
just have
so for all this carry outs,
logical expressions
directly write
in
so
this
diagram and calling
this
that block as the carry generator. So that is what I have done here. You can just
the carry generator
and draw the circuit. So this is what it looks like. So now basically we are looking at the addition of the two inputs A and B. So in order to complete the entire circuit for this addition, so we'll do the same. So we'll complete the circuit here.
This
carry so anyway
in terms of the
Boolean C0 is our input, which will be directly given to this carry generator circuits. And as we have seen, this G0 is nothing but the ending of A0 and B0. So we will be receiving the inputs of A0 and B0, so that we will be ending and giving to our generator circuit. And so this is basically A0. So actually it is not very clear here. A0 and B0, and the XORing I have given it to P0, and similarly the same thing we need to do. So the XOR of A1 and B1 is nothing but our P1, and their ending is our G1. Ending is our G1. Similarly, the XOR will require one XOR and one AND gate whose inputs are A2 and B2. So the XOR is output is given to P2 and the ANDing is given to G2. Similarly, I require one more AND gate. This diagram looks very clumsy, but you can draw it very neatly if you just sit and B3. So the XOR is connected to P3 and the ANDing is connected to G3. So this is what, and we need to realize S3, S2, S1 and S0. If you recall, the sum expression is nothing but A XOR B XOR C. So for the initial sum it is equal to it is the diagram is looking very clumsy, but I can see you can take this C0 out here. C0 you can take out here, and let us say my P0 is also available with me, P0. So if I just do the XOR operation here, I will get my S0. This P0 is nothing but this whatever I can, so I can actually draw a wire here. It looks very clumsy, so I am assuming that P0 is available here, and similarly my S0 will be the XOR of P1 with C1. So this is my S1, where this P1 is nothing but this expression, that is A1 XORed with P1. That anyway it is so we need to draw a wire here as mentioned previously. So I am assuming that P1 is available here, and similarly C1 is calculated so like this, that is a carry generator. Similarly I am assuming the P2 is also available with me, so this XORing will directly give me S2. Similarly S4, this is nothing but my P3. So this is what the phone, and we don't have so this C4 is nothing but our like 5th bit. So this is our 5th bit. So this is the overall carry look a radar would look like. Now as you can see, now we are more interested in the delay, right? So as you can see, so let us divide the entire logic into 3 stages. So let us consider this to be the stage 1, and the carry generator to be the stage 2, and the remaining to be the stage 3. So in stage 1, I will highlight with the marker. So in stage 1 here, up to this stage 1 here, the delay is equal to the maximum. So from the inputs to here, the delay is equal to the maximum of the delay of XOR gate and AND gate, which will, so obviously the delay of XOR gate will be more than the AND gate. So I am directly writing here it is equal to the delay of XOR gate up to that stage 1. So let us consider this CLA to be the carry look ahead adder, and TCLA is the delay of the carry look ahead adder, and up to stage 1 it is equal to T XOR gate plus, in this carry generator you can see, so this is so this stage will require the maximum delay. I will highlight here. So this stage will require the maximum delay. You can also check here. I mean, why? Because for generating C4 we need to pass we are having a maximum delay of a 5 input AND gate along with the 4 input OR gate, when compared to the previous delays of C3, C2, C1. For C3 we require a maximum of a 3 input AND gate and a 4 input OR gate, which will obviously be less than the delay that will be generated for C4. So this will actually determine the delay for my carry generator state. So that is equal to the delay of 5 input AND gate and a 5 input OR gate. So I am writing it here. So that is equal to the delay of 5 input AND gate. Let us call this to be 5 and 5, and delay of 5 input OR gate, and let us call it as 5. And so this is the delay of my carry generator section. So these two terms denote the delay of my carry generator section, and in the last stage, that is this stage, that is after the carry generator stage, obviously it is the delay of the XOR gate, so that I am writing it here. This is T XOR. Now this is equal to T XOR, and T XOR I am directly writing it here as 2 times T XOR plus, let us assume that I am realizing the 5 input AND gate with 4 2 input AND gates. So I am directly writing here 4 times the delay of 2 input AND gates, that is T AND. And similarly the 5 input OR gate is realized by using 4 input OR gates, 4 2 input OR gates. So that way I am writing 4 times 2 input OR gate. So let us assume that the delay of AND and OR to be same. So we can just let us assume practically it will be different, but let us assume that it is equal, and so replacing T AND with TR, so it will be 4 plus 4, 8 times of TR. So the total delay of carry look ahead adder is equal to 2 times the delay of XOR plus 8 times the delay of OR gate, 8 times the delay of OR gate. So this is the expression now we have got. We will compare this with that of the carry look ahead adder. When we go to the previous sections, we have realized the delay expression for the adder. So here we have written the delay for the triple carry adder is 8 times of XOR plus 4 times of OR gate. So let us write that expression here. The delay for RCA, that is triple carry adder, is equal to 8 times that of XOR plus 4 times that of OR gate, which is very much less than which so the delay of carry look ahead adder is very much less than when compared to the delay of the triple carry adder. Here we require only 2 XORs, and here we require 8 XOR. This itself will occupy, even if we neglect the delay of this OR gate to be 0 and 0. So the delay of the carry look ahead adder just requires 2 XOR gate delays, while that of triple carry adder requires a delay of 8 XOR gates. So this is why carry look ahead adder is very much faster when compared to the ripple carry adder. So this is what so this is the end of carry look ahead adder. So